Here is a little more detail on computing the mean residual life function, L of t, which is defined as the expected value of big T minus little t given t is greater than or equal to t for this particular distribution given by this probability mass function. Let's start out with L of 0. Now L of 0 is the special case, which is the expected value of t. So the one special case can be found just by taking the sum of all the mass values, that's 3, 4, and 7, times their associated probabilities. So this is going to be 3 multiplied by 0.5 plus 4 multiplied by 0.3 plus 7 multiplied by 0.2. And when you work that out, the expected time to failure for this probability distribution is 4.1. Now, not surprisingly, that 4.1 has got to fall somewhere between 3 and 7. So that's just a quick check to make sure that's right. So L of 0 is 4.1, which means between time 0 and the first mass value, which is time 3, this mean residual life function will decrease linearly with a slope of -1. So it's going to go from 4.1 down to 1.1. But then at time 3, we want to see what's happening. And actually, we want to see what's happening just after time 3. So some authors use this kind of unusual notation, L of 3 plus 0. Well, what this is, it's 1 over the survivor function, so it's going to be 1 over 0.5, and then that will get multiplied by the summation. And in this case, we have 4 multiplied by 0.3. The mass value of 3 is out of the picture now, plus 7 times 0.2. And here's the part that's easy to forget. This is mean residual life, so we subtract out 3 from that quantity. When you work out the arithmetic here, this turns out to be 2.2. Finally, the last piece between time 3 and time 4, this will decrease from 2.2 down to 1.2. And then at time 1.2, it jumps upwards again, so we're trying to figure out L of 4 plus 0. That's the value of the mean residual life function just to the right of 4. So in this case, we once again take 1 over the survivor function, that's 1 over 0.2, multiplied by the summation, but this time the summation is just 7 times 0.2. You can see the 0.2s are going to cancel there, so you're just going to get 7. And once again, you subtract off t, which in this case is 4. 7 minus 4 gives you 3. So the mean residual life just epsilon to the right of 4 is 3. Now, what happens between t equals 4 and t equals 7? Well, over those 3 time units, this thing is going to go from 3 down to 0, and that's the picture that we had on the previous slide. Here are 3 discrete lifetime results. If you remember from the continuous case, when we had the survivor function and we wanted the probability density function, we differentiated. So it won't surprise you that in the discrete lifetime case, to go from survivor function to probability mass function, you take a difference rather than a derivative. Second result, you know that the hazard function at time tj is the ratio of the probability mass function to the survivor function at tj. But from result 1, we know that we can rewrite the numerator here as s of tj minus s of tj plus 1. Now we have a hazard function written entirely in terms of the survivor function. If you want to simplify this a little bit, you can see s of tj divided by s of tj is 1, and you get this expression right here. If you go ahead and solve that expression for s of tj plus 1, this can also be written in this fashion right here. Finally, the last result, which again involves survivor functions and hazard functions, and this is proven in Appendix F of the book. S of t is the product over all j such that tj is less than t of 1 minus h of tj, once again for t values greater than 0. This particular result is going to lead to something called the Kaplan-Meier product limit estimator, sometimes abbreviated KME. This was discovered back in 1958, and this particular result for many years was the #1 most cited paper in statistics. We will talk more about the Kaplan-Meier product limit estimator in Chapter 10. Here is one final example of a discrete distribution for a time to failure which could be used in reliability, and this is the geometric distribution. It is defined by a probability mass function f of tj is p times 1 minus p to the j minus 1 for j equals 1, 2, 3, etc. And the parameter p here must satisfy 0 is less than p is less than 1. So that is some fraction between 0 and 1. Now, there are two different flavors of the geometric distribution. One of them starts at 0 and the other one starts at 1. So because this one starts at 1, it is more likely to be used in a reliability application, because if you have a brand new item like a light switch, you have a first demand on the light switch, the first cycle, and then a second cycle, and then a third cycle. So this time, the support is just the positive integers. The interpretation here is this is the trial number of the first failure in repeated independent Bernoulli trials, where P is the probability of failure on each trial. Now, when you learn the geometric distribution, you typically learned P is the probability of success. We switch that in this case because failure is of interest when you are doing reliability. So quick note, we don't have just any demand value on the system. We have 1, 2, 3, 4, unlike the previous example where we had the very unusual 3, 4, and 7 as our mass values. This time it's just 1, 2, 3, 4, etc. Well, the survivor function in this case is defined exactly the same way in the discrete and continuous cases. However, for a discrete random variable, rather than being an integral, it is a summation. And so all we have to do is take that geometric probability mass function, place it in the summation, and that's as far as we can go. However, if we're willing to throw in a little more notation and let k be basically the lower limit in that summation, when you do that, this summation is going to go from k down on the bottom up to infinity. So in that case, what you get is you get the survivor function is this particular sum just by writing out the terms. Each one of those terms contains a 1 minus p to the k minus 1 times p, so that can be pulled out, and what's left is a geometric series. The common ratio there, 1 minus p, falls between 0 and 1, so that geometric series is going to sum to 1 divided by 1 minus the common ratio, and you can see that the common ratio is 1 minus p, so that whole thing reduces to 1 over p, and the 1 over p cancels with this p right here, and we're left with this very nice looking survivor function for the geometric distribution. So we were given the probability mass function. We have found the survivor function. Let's keep going through the list. The hazard function in the discrete case is the ratio of the probability mass function at Tj to the survivor function at Tj. The mass function is given by the numerator here, p times 1 minus p to the j minus 1. The denominator we just saw was 1 minus p to the j minus 1. The two terms here cancel, and you're just left with p. So this turns out to be the only discrete distribution that has a hazard function which is constant, and so that is the memoryless property. So to review here, the exponential distribution was the only continuous distribution with the memoryless property, and the geometric distribution is the only discrete distribution with the memoryless property. So we've done 3 of the 5 so far. Let's go to the next one. Capital H of t. Remember, there was a dilemma defining this thing. We decided to stick with the opposite of the natural log of s of t. Log is used here in the slides. In the book, that's been changed to ln in the 3rd edition. And that turns out to be minus k times the log of 1 minus p, where k is defined as before, being the smallest j such that tj is greater than or equal to t. Finally, without going through the steps, after some algebra, L of t, which is defined to be the expected value of t minus t, given t is greater than or equal to t, is 1 over p minus t minus the floor of the time, where that floor is the greatest integer function. Now, to take a look at the pictures on these things, here is the geometric distribution with one particular value of p, and this value of p is 0.4. So first of all, it looks like it's cut off here. For the probability density function, you can see the initial spike here is at p, which is 0.4, and then the next spike will be 60% of that, so that's 0.6 times 0.4. The next spike will be 0.6 times 0.6 times 0.4, etc. And you get that kind of classic geometric decline. The second thing we have plotted here, this is the survivor function. And notice the survivor function starts at 1, as you would expect. And even though it's not given here, this right here would be a closed point, and this would be an open point, and that continues downwards. The first step downwards here is going to be the 0.4. So this distance right here is 0.4, and then the next one has a spike of 0.6 times 0.4, that is 0.24, and that is this downward step height. So each step downwards corresponds to the height of the mass values in the probability mass function. The next one, the hazard function, always has a value of p, and since p is equal to 0.4 here, each one of these hazard function spikes is 0.4. That's the same as saying if this is a light switch, every single time you flick that light switch, there is an equal probability that it will fail on that particular trial. So once again, the interpretation is if the light switch is working, there is a equal probability chance on each flip that it will fail. Here is the cumulative hazard function, and you'll notice that each one of these steps upwards has the same height, and that is consistent with a constant hazard function. Finally, the mean residual life, let's just do L of 0 real quick. L of 0 is that one special case of the mean residual life, and it is the expected value of t. Somewhere, hopefully, in a probability course, you have derived that for the geometric distribution starting from 1 as 1 over p, and 1 over p in this case is 1 over 0.4. 0.4 is 2/5, so we get 5 halves, which is 2.5, and that's where the geometric distribution starts, right there at 2.5 at time 0. What does the mean residual life function do? It goes down with a slope of -1 between demands, and then each time it just jumps from 1.5 back up to 2.5, and that sawtooth will continue out to infinity. Remember, this is an item which simply does not age, and that's the memoryless property. Finally, the last thing in this section are mixed distributions. And mixed distributions are really mixed discrete continuous distributions. They are part discrete and part continuous. I draw one here where we have time on the horizontal axis and a survivor function. And the discrete portion is right here, and that's where you see the jump. So that is the discrete portion. And then the continuous portion is the rest of it. To give you a reliability example, if you have light bulbs which are not very reliable, in that 10% of them fail immediately, that corresponds to this jump here from 1 to 0.9. Outside of reliability, you can have the daily rainfall at a particular location. Now, in this case, that location would be a very rainy location because 10% of the days you get no rain, whereas 90% of the days you get rain, but the amount of rain is controlled by this survivor function. Finally, the last one in queuing theory, the delay time in a single server queue. So this is how long you have to wait in the queue. And it might be the case that there are 10% of the customers, these lucky ones right here, they don't have to wait at all. And then the 90% of unlucky ones wait, and that follows this particular survivor function here. That's an example of a mixed distribution, part discrete, part continuous combined. Now the next section goes to moments and fractiles, and those are important quantities that do not completely define a distribution, but they are a single number that gives you perhaps the center or a fractile of the distribution.